Okay, Siang Hwee, please start.
Okay, thank you. So good afternoon all. Today I'll be presenting on execution reconstruction, harnessing failure reoccurrences for failure reproduction. Okay, so this paper was written by 6 authors. The first batch of the 6 authors, 3 of them are here. These 3 are all PhD students from the University of Michigan. And the similarity between all 3 of them is that they have a shared focus area in reliability of softwares and reliability of instructions, which is why they actually came out with this paper. Yeah. Then the other 3 authors, they are professors and assistant professors from different universities. Similarly, they also have a focus area in this kind of reliable systems. Yeah.
Okay, please go ahead.
Yeah. Okay, so some background on this paper. The main idea of this paper is they want to reproduce failure. So take note that the idea is to reproduce failure and not to actually solve this kind of failures. Yeah. So the reason why they want to do this kind of failure reproduction is because it's very critical for software reliability. It's very useful for debugging if you know what are the inputs that results in failure. And it actually allows you to use a lot of higher level tools like your debugging itself, as well as security, forensic, and other kinds of tools. Yeah. Mainly, it's very valuable for production code because sometimes the error might only occur when you have already deployed, and it might not be easy to replicate it in-house.
Yeah, so I have just one comment here. So I think not every student here is focused on debugging research, but debugging is Siang Hwee and Yuchen's FYP. Actually, Siang Hwee's FYP topics. So in order to aspect for the debugging research, the ultimate goal is to automate the process of debugging. If, for example, we know there's a bug happens, we want to automatically locate where is this root cause and why it happens. So that's for research. But apart from the research, I think for every student, you have to write the code. So understanding how automated the debugging approach works may also have some practical value for all of us to understand how to debug our own code. And here, one of the most important or fundamental problem of debugging is about the failure reproduction. So if we want to debug or locate a bug or locate a root cause, we have to make sure this bug is replicable or reproducible, right? And then, of course, for some sequential programs or our algorithms, so the bug is always replicable. Each time we run, it will crash. So that will be easy. But here, for some other cases, for example, the distributed system or concurrent systems, it is not necessarily the truth. It isn't necessarily true because once we run the program, the bug it's just gone, and we run again, the bug appears. And so here, this research is to it's just about focus on failure reproduction and when the bug happens and how do we reproduce the failures and to provide a steady environment to debug. Okay, please go
on. So the problem that they are trying to solve is that currently there are actually some systems out there that are meant to do this kind of failure reproduction. However, this system actually sacrifices on at least one of these 3 goals. So efficiency, which is the amount of resources required to reproduce the failures. The effectiveness, which is the capability to reproduce different kinds of bugs. So there are concurrency bugs, there are bugs where the failure and root cause are very distant from each other. And then there's accuracy, where whether the control flow and the data values can be recovered correctly. Yeah, so right now, some of the systems out there are like the record and replay system. So the idea behind the record and replay system is that it records the entire execution of software, and then it plays back to diagnose and to resolve any defects. Then there are also hybrid methods, which does like some form of hardware tracing, as well as static analysis of the code to retrieve the data values. So the bad thing about it actually overwrites the state frequently. Yeah. So one question for the audience: between these two systems that I mentioned, what does each of the system actually sacrifices? Yeah.
Okay, it seems good. It looks like a very good question. So maybe you can point out audience and have a try.
Okay. I think Yufan, maybe.
What does each system sacrifice?
Yeah, so out of these three goals that we are trying to achieve, right? Each of these systems are actually lacking in a certain of this goal. That's why we are trying to come up with a new system to implement all three goals. Yeah. You can take a guess. Like,
Okay.
so, yeah.
Maybe not.
Yeah, the record and replace system first.
Okay, so the record replace system record the entire execution of software. So maybe it's lack of efficiency because he needed to record all the execution. Is
Yes.
it right?
Correct. Yeah, that's correct. And maybe for this one, it's a hardware tracing and it overrides the state frequently.
Okay, so maybe the accuracy or
yeah, actually it's the efficiency and the accuracy. Yeah, so you got both correct. Yeah. So for the record replace system, because it records the entire execution, it's actually not very efficient. So imagine if you have like 3 million lines of code, kind of code base, it's going to be not very efficient to record the entire execution. Then for the other two, the kind that's a bit of a hybrid, currently is actually overwriting the state very frequently. So sometimes we might not be able to recover the data values correctly.
So so maybe you can be more specific on the state. What does the state mean? The proven state or?
It's the state at which, so it's like it includes the data values. So what are the variables? What are the values currently in the variables? As well as, yeah, mainly is that lah, and which line of code.
Yeah. Here, so can you be more specific of what these REPT or POMP abbreviated for?
Okay, REPT okay. REPT is a paper that was written recently. I don't know what REPT stands for. It's reverse debugging of failures in deployed software. It's written by Microsoft Research and Michigan. And yeah, they never actually explain what REPT is. I believe REPT is the name of the program itself. And regarding this REPT, it's also it's a closed source software. So actually, they only have a paper that is produced on it. And this paper, the current paper that we are discussing on, actually just compares their result against this REPT software. Yeah, the actual mechanics of how REPT works, I'm not too sure because it's not the focus of this paper. It's just that it make use of, it's a hybrid model. So it's a online plus offline kind of model. Yeah.
Maybe I can have a guess because on our research, Siang Hwee, Yuchen, and I, the researcher focused on record and replace systems. And for the REPT or REPT systems, based on the description of Siang Hwee, it is probably a technique of reverse execution. So usually we write a programs line by line, and the interpreter or the interpreter or the compilers actually will execute the program line by line, right? So one of the important problem of debugging that we want to investigate the events happens before. For example, we will find there's a crime happens on the street. Of course, we need to analyzing what happens before, and then we can conclude what is the root cause for the crime happened. Maybe there's a murder or there's a theft there. So similarly, when we are debugging programs, we're trying to investigating why observe the failure happens. In this case, we need to go back to the time past. So usually the record and replace system also will call the time traveling systems. That means we travel back to the past and understand what is the root cause. And of course, record and replay is one way to record what happened in the past. And another technique might be reverse execution. So in this case, when the programs are executed line by line, and we will want, when we find there something happens or there's something unexpected happens, and we want to know the past. In this case, we do not record everything because, as Yufan has guessed, record and replace system will have a large overhead on the runtime efficiency. So in this case, we do not record a lot of stuff. But we have a technique to reverse execution line by line in a reverse order so that it can find the past. So that's the basic idea. But anyway, if we want to reverse executions, it will have it still have some overhead, and also will incur some has overhead on the accuracy. But I think if we execute it well or the system design well, the accuracy is supposed to be preserved. So I do not know specific how the IPT or POP technique are implemented, but basically it is kind of a reverse execution technique. Okay, please go on.
So yeah, so actually one of the main challenges of this, as Dr. Liu has mentioned, is that there are many possible control flows and variables in a program itself. So actually to isolate down to what is causing the issue is also not going to be very easy. And because of it, we want a system that is able to be efficient as well as accurately pinpoint the arguments that make it fail. Yeah. So because of that, they actually proposed this thing. It's called a execution reconstruction system. So it makes use of hybrid offline and
here, Siang Hwee, so there's a question raised by Darren. So what about non-deterministic bugs?
Non-deterministic bugs like what?
Yeah, I think Darren can be more specific on that.
Like what about like bugs that only appear under certain conditions? So like certain conditions governed by some random process, for example. Because I believe the earlier two methods won't work for those, right?
Okay, so I mean, based on what I'm understanding, is like maybe you are saying like a bug that occurs due to other external factors, is it?
I mean, you just take like a black box example. Maybe we have some code, some branch that only executes based on some random generator, and it executes maybe like 5% of the time. So that bug only appears 5% of the time.
Yes, because Darren is working on definitely a non-deterministic project called event suite, right? So if we want to debug event suite, how this technique is supposed to be helpful? Okay, Siang Hwee, you can have a try to answer the question.
Okay, the thing is, right, given that the idea behind this execution reconstruction is that the moment it detects a failure, it will so-called try to figure out what is the error with regards to it. Okay, with regards to your question, I agree that the previous two methods, at least the replay method, if you are lucky enough to get to record and replay the entire system when there's a bug, I'm pretty sure you should be able to isolate down to what specific variable, randomly generated number that creates the problem, and maybe that way you can do some form of debugging. I think that might work for the so-called non-deterministic bugs.
Maybe I have a comment here. So the idea of record and replace, so here this work is called a reconstruction. So I think reconstruction serves two goals. The first is that for record and replay, we do not need to record everything. We just need to record some specific parts, and then after we just record a specific or the key components. Once the key components recorded, we can just recover the rest of those. And the second might be just to address Darren's concern, especially why we need to record and replay. And one of the benefits is that if it is non-deterministic programs, the bug may disappear next time we execute it. So in this way, if we can run the system multiple times, with record and replay debugging technique. So as long as one bug appears for one record and replay session, we just need to look at the trace of record and replay system, and there's no need to re-execute it again, right? Because everything making such a bug happens has been recorded. So in this case, especially for this reconstruction technique, we just need to have some lightweighted recordings so that we can replicate the rest of the execution traces to replicate the bug. In this case, maybe in this record and replace system, it will find that the random generator seed will be one of the most important components will be recorded. So in this case, when reconstruction or re-executed systems, it will, whatever the random generator will be produced, it will always use the recorded seed to re-executing the program. That's my guess, but that is makes possible. So the idea is to replicate the bug.
Yeah.
Have I explained myself?
Yeah, I think it makes sense. Thanks.
Yeah, I think in the future we can consider build a system, record and replace system for EVA Suite, because EVA Suite is really hard to get out, right?
Yeah, that's kind of one of the reasons why I was a bit curious as to
Okay.
Yeah, maybe today's system might be useful. Yeah, because today's system is a hybrid between the two. So maybe if later I'll go into the details and maybe you might find it useful.
Yeah, but anyways, the record replace system maybe a little bit difficult to analyzing the program analysis system. So if it is a normal program, such a record replace system can work well, but because it usually uses a code instrumentation technique. However, EVA Suite is a system which also uses instrumentation system. So for an implementation level, I'm not sure how we instrument a program will leverage instrumentation per se. So that will be a technical concern, or it's more like a recursive progress. Okay. Okay, let's keep going on.
Okay, I'll carry on. So yeah, so execution reconstruction, or I will just term it as ER, is a hybrid offline and online failure reproduction technique. So online failure reproduction technique is actually a runtime recording. So it actually runs the code and records certain aspects of the code. While offline is actually a static analysis of the code itself. So there's no running of the code involved. Yeah. So based on this online and offline recordings and analysis, it actually determine a subset of execution information, which is inexpensive to monitor, and it's useful for the failure reproduction later. Yeah. So it actually makes use of these two techniques. First one is a shepherded symbolic execution, and the second one is a key data value selection. So I will go into further details with regards to these 2 points later, because they are actually the bulk of this execution reconstruction. Yeah, and with this execution reconstruction, they are actually able to manage to hit a sweet spot of the trade-off between accuracy, efficiency, and effectiveness. Yeah. So just a diagram or.
Oh, by the way, so can you further strengthen the difference between effectiveness and accuracy?
Oh, effectiveness and accuracy, right? Okay. So effectiveness is it's able to reproduce different kinds of bugs. So I might have, for example, like non-deterministic bugs or concurrency bugs, or bugs where actually a normal, maybe like a overflow error. That those are how many kinds of, okay, so effectiveness is how many kinds of bugs I can detect. Accuracy is whether the bug I detect is actually the bug. Yeah. Is it clear like that? So effectiveness is
but here is not about finding a bug. Here it's just a reconstruction to execution, right?
So correct. So
so I'm just wondering.
Okay, so
the difference between effectiveness to reconstruct execution and the accuracy to reconstruct execution. So what's their difference?
Okay. Yeah. Yeah, I think it's still the same thing, that effectiveness is how many kinds of bugs I can catch.
Or
Based on
how
my current
many-
system, how many kinds of different bugs I can catch. While accuracy is after I experience a
but
failure.
the system will not report whether there's a bug, right? For this, it's not the focus of this work to report what kind of bug it is. It's just to reconstruction.
Yeah, correct. So maybe I can reconstruct, like I can reconstruct concurrency bugs. I can reconstruct failure bugs, but I cannot reconstruct certain other kinds of bugs. So that is how effective is it. Then accuracy is more of, let's say I want to reconstruct the concurrency bug. So these are the inputs, and whether these inputs that is given actually result in the exact same bug that we experience. So it's slightly different in that effectiveness is, like I say, is how many bugs you are able to.
It seems to me that the effectiveness is kind of equivalent to applicability. So on how many application or scenarios can this system or can this technique to be applied on them? And accuracy is that for given applications,
yes,
and how accurate can I really reconstruct it?
Yes,
right?
correct.
Okay, next, keep going on.
Yeah. Okay. So this is the flowchart of how execution reconstruction goes. So at the initial phase, they will run the program. After running the program, during the program runtime, it will actually do a control flow recording. So it will keep track of which branches the program actually takes. Then upon hitting a failure or maybe facing some error, this control flow is actually passed on to this shepherded symbolic execution. So this symbolic execution will try to do some it will try to identify what are the constraints that result in the failure happening. And then if it's able to successfully reproduce the failure from this stage, it will just generate out the test case. If not, it will, for example, if there are way too many constraints, then it will go into a key data value selection to select out specific, more important variables to be passed back into this program. And now the program will keep track of the control flow as well as the variables that are deemed to be important. Yeah. Is it clear for now? Is the system clear for now?
I get a general picture, but I think for the audience. So do you have any description or introductions about symbolic execution?
Okay, yeah. So
and also there's a term, because this is my first time to learn Shepard. Shepard. So symbolic execution.
Yeah, okay. That one I'll go into greater detail. So for now we can it's to show you the idea of how the flow from the program running to what are the steps that it takes for it to do the test case generation. Yeah, but as I mentioned, these two are the main focus, so I will go
by the way, if it is a non-deterministic programs, even we generate the same test cases may lead to different control flow, right?
Correct. So I was thinking that because in this key data value selection, it actually take note of important variables. So maybe the so-called seed or the random number that is generated can be recorded in this key data value selection. And then we are able to identify what are the so-called random values that actually result in a test case failing. So I was thinking maybe this part would be applicable to the non-deterministic bugs.
Yeah, okay. So it's great. So maybe you can introduce symbolic execution later, and I think I can make some comments and try to further explain it. Okay.
Okay, can. Okay, so as mentioned, online monitoring, which is the first part of it, the online monitoring portion, it uses runtime and driver support to actually monitor any production failure. So by default, it actually traces all the control flow that.
No, by the way, sorry for interrupting.
Yeah.
So there are implementations on Java or C++ program or the binary.
Sorry, their implementation, like their tools implementation, right? Or
there are tools for implementation. So anyway, the technique to support Java programs will be very different to support the binary program, right? So what's their? Have you go through their or checks their implementation?
Their implementation, if okay, they actually, because they build onto existing systems. If I'm not wrong, it's in terms of C++. Yeah.
C++. Okay.
If I'm not wrong, but I would have to double check that. Yeah.
Yeah, because there's different symbolic execution engines for Java, C++, maybe for Python. I don't know. I think Python is supposed to have very enriched library. I think symbolic execution would not be a problem. Okay, please go on.
Yeah. Okay. Sure. So yeah. Then this online monitoring, it records all the control flow and the data values during the execution of the program. Yeah, so by default, it actually traces all the control flows that the program actually takes to prevent path explosion, which I will explain later. Yeah, path explosion is a problem due to the many branches that a program can take. So when the failure is detected, then these runtime traces passed to the Sheparded symbolic execution. Yes, correct. Okay. So moving on to the Sheparded symbolic execution. But before that, we will touch on symbolic execution. So what is symbolic execution actually? So if we look at this short Python code that I have over here, it's very clear cut. So there's a fail situation and a succeed situation. So how symbolic execution works is that it actually do not pass in anything to the function. There's no value that's passed into the value. Instead, it's a symbolic value. So for this case, maybe we will have a symbolic value x. Then when x is passed into the system, it will actually go through everything. So z will become 2 times x. And then at the branch over here, it will actually go into both branches with the value of z being x times 2. So after that, when it checks the fail condition, it will actually solve for x. So we know that in this case, if we will only enter this branch if z is equal to 12, which means that x is equal to 6. Yeah. So from this, we can actually determine what are the constraints of a program. So for example, for me to enter this branch, I must be 6. Otherwise, I will always enter this branch. Yeah. Is it clear? Do you all have any questions regarding symbolic execution? So the idea is it will explore all the branches that are in this program, and then it will come up with the so-called constraints for each of these branches.
It's quite clear to me, but I think you can, if possible, you can have some questions for the audience for them to digest here.
Okay, can maybe, yeah, okay. Maybe we'll move on for now. I will come back to symbolic execution later with a bigger code snippet. Yeah.
Okay, sure.
Yeah. So maybe one question first. What is the problem in this case of a symbolic execution? Yeah, actually I think this is a pretty easy question. So because there are many conditional statements, actually it will lead to something called known as path explosion. So for now, it's just a short little code snippet. So there are actually only 2 paths that it can take. But imagine if I have multiple if-else loops within this if-else block itself. So actually, it will lead to a lot of paths that it could possibly take. And this will result in a lot of computing resources to actually calculate what are the different constraints. Yeah, so because of that, symbolic execution on its own is not sufficient, which is why they came up with something called as Sheparded symbolic execution. So the idea behind the Sheparded symbolic execution is that it actually makes use of the traces that was produced during the online monitoring. So because the traces that are produced during the online monitoring, it already takes into account the control flow. So if we use the previous example, the the tracers will actually tell you that, oh, I'll go into line 1, line 2, line 3, and line 4. So we actually have a very clear path of what is the condition that's required to hit the failure condition. So the idea behind the shepherded symbolic execution is as such. So we just need to follow one path instead of multiple paths. Then based on that one path, we actually gather all the constraints on the input variable. So in the previous example, the constraint is that if x is equal to 6, it means that my program will fail. So because we are only going down one path that is guaranteed to lead to failure, we actually will eliminate any of these path explosion problem. Yeah. So that is the reason why it's shepherded, because it's guided based on the traces that are produced during the online monitoring. Any questions with regards to this?
I think I'm fairly clear on these parts. I think there are several problems for symbolic execution. Can you go back to the previous slide?
Oh, sure.
Yeah, so here I think, of course, the path explosion is definitely one of the most notorious problems introduced by symbolic execution. And actually, there's some other issues like the path conditions. Here, z is assigned by y times 2, right?
Yeah.
Suppose the value of y times 2 is not, suppose the left-hand expressions is not a y times 2. It is come from a socket communication. In this case, the path condition here will not be available, right? Will not be available. So this is the problem of the missing or incomplete path condition problem. And also here, there's if else. Suppose there's condition is including while or for loop. In this case, it becomes hard to track how many loops should we enroll here, right? So this is another problem because when we have a loop, because everything is actually symbolic, it's a symbol. So we never know how many loops will be, how many iterations will the loop will be executed. So here, the question is that, of course, we have execution here. And how the symbolic execution address the incomplete path condition problem. So for example, the y times 2 is not y times 2. It actually comes from the socket request or socket response. And how do they handle, how do they build the constraints based on such a condition?
So that means instead of y times 2 is like a socket.receive kind of thing.
Yeah.
So z will become the input, so to speak. I mean,
but anyway, the socket could be using y as input.
Yeah, correct. But whatever it is, okay, I'm not too sure how they approach these kind of problems, but if from my perspective is that the part where it takes in this kind of input would be outside of this function block.
Definitely.
So actually, from the perspective of this function block itself, it's still just taking in an input. So if let's say now I'm taking in an input from a socket somewhere else, I mean, if the input that comes in is incorrect or incomplete, then the problem, the issue will be raised at that point itself. Correct.
So I'm thinking about whether, since you still have the key value selection, right? There's a technique for key value selection.
Yes, correct.
I think the question I raised probably will need to turn to the key value selection part. If we have the key value selection part, whether symbolic execution or such a Shepard, the Shepard symbolic execution is still necessary. Because we just need to keep track of all the key values and we can just replicate the execution, right? So for example, if y times 2 is replaced by a socket.receive, in this case, we just need to record what value is returned by the socket, right? So we can keep going on, we can just keep it on. In this case, whether such a symbolic execution was still, is that symbolic execution really necessary?
It's still necessary because, for example, in this case, I do not want to keep track of every variable. correct. So I mean, for now I only have two variables, y and z. But for example, in a program that has a lot more variables, I do not want to keep track of every variable that comes in.
Yeah,
so
but I know, but symbolic execution was usually used for. I think symbolic execution is very popular in academia, but in practice, so people will call library will call their library. So in this case, the path explosions and missing missing path conditions is very common. So in this case, and what role played in symbolic execution? So for example, as long as I think the symbolic execution can only be usable for partial paths, right?
Yes, correct. That's why it's a iterative loop.
Oh,
so
I got it.
The symbolic execution will pass the information down to the key data value selection. So it's actually a loop like that if it's not able to reproduce the failure.
So basically, if they find symbolic execution, there's a missing variables, they just using key value selections.
Then
But once,
then
we find the path, then they find the path there, and they just using symbolic execution. So the basic idea of symbolic execution is just to trade the logics, using the logics to replace recorded value, so that we can lower the overhead.
Yes, correct.
Of the execution.
Yeah, that's why we would like to use symbolic execution, so that if we can minimize the number of variables that we are keeping track of, we want to minimize it.
So in this case, the symbolic execution is conducted during runtimes, or
sorry.
So the symbolic execution is executed during the runtime.
No, it's only after the failure. Yeah, then it's done in the offline phase. So the only thing that is being on this side during when it's during the runtime, what is being kept track of is the control flow, as well as certain values that are already selected. So
that means does that mean that they need to re-execute the program again?
Yes, correct. So that's why it's actually
and so here comes the problem. If we re-execute the program again, we may not get the same trace anymore. Right, just like Darren the question raised by Darren. So
correct. For the
again, the path is not because it's supposed to be a non-deterministic program.
Okay, yeah, correct. That's fair, because the idea behind this is that you need to at least run it a few times. Based on their experiments, it's not a one pass. It's very rare for it to be a one pass thing. Most of it is about a 2 or 3 pass before it's able to generate the test case. So in a non-deterministic bugs, yes, it might be a bit hard to do it multiple pass. Yeah, I agree with that. So this might not be very practical for the non-deterministic bug issue. Depending
and also I still have a question here. So
yeah, sure.
Since symbolic execution, for example, the symbolic execution, if it's really powerful and there's no missing variables or missing path conditions during the symbolic executions, so the symbolic execution will generate the test cases, right? But the point is that we have already known what test cases can reduce the bug.
Yes, correct.
So there's no necessary to generate the test case.
Yes, correct. Actually,
right, the test case we have already known what test case are. Correct. We just need to keep rerun the test case, and that's all.
So the I think the idea behind it is that because it's in a production, it's when it's already being in a production scenario. So for example,
and also I have a question that suppose we record everything, what is how many times we can slow down? So if we can just slow down the execution for maybe less than 10 times, I think it's okay for us to record everything, right?
Sorry, what do you mean by slow down?
Slowdown is that about efficiency. So suppose the idea is that, for example, we run it, and we want to. The basic idea, if I understand correctly, is to make less instrumentation, as less instrumentation as possible. So if we instrument everything, the runtime execution, the overhead of runtime executions will increase a lot, right? Suppose we instrument everything, then and the program actually will have maybe 10 times or 20 times or even 100 times instruction more, because we need those instructions to record everything. So in this case, it will only require very little or less number of instructions for instrumentation, so that we can have a less overhead or less execution overhead. So that is what I mean by a slowdown.
Slowdown. Okay.
Right. So in this case, if the slowdown, the times for slowdown is not that serious, it's not that severe, there's no need to do this, right? We just need to record every variables. And the ultimate role played by the Shepard execution, simple execution, is just to reduce the number of variables to be selected or to be stored there. Is that the case? Consider this.
Yes, correct.
So,
it's just to reduce the number of variables that are being stored. Correct. It's to the symbolic execution part. If it's able to identify the constraints very clearly, then yes, it will be able to generate the test case. So later I can show an example of how it can generate the test case. So I agree with you that if I already have a input that results in a failure, then what's the point of generating a test case? But I believe it's because in a production environment, certain variables might result in it being buggy. And the same.
So what I mean is that we record the trace, but we do not record the input.
Correct. I think for the first run we will record only the trace.
But I think it is cheap just to record input.
The input as well.
And how expensive to record inputs, right?
Yeah. For them, they are by default they only record the control flow traces. They do not actually record the inputs. If I'm not wrong.
From the very initial execution, they do not record any variables.
Yes.
They only recorded the branches or control flow.
The branches that are taken.
And then they try to using symbolic execution to recover the variable.
Yes.
And if they cannot be recovered by the
they will take notes of the symbols that are important. So for example, like in this case, they will know that y is important. So in the next run, it will take in the value of y, something along that line. Yeah.
Okay, you can keep going on.
Okay, yeah, let me carry on a bit. Okay, so yeah.
Okay, so there's a question raised by Darren. So that symbol execution. So do you have any further explanation of symbol executions, or if not, I can make some comments here.
Regarding symbolic execution?
Yeah, there are more explanation of symbol execution.
Let me see.
Do you have any other explanation there? If not, I can.
No. Yeah.
Okay, so maybe I can start making some brief explanation of symbol execution.
Okay.
So the concept of symbol execution is actually correspond to the concrete execution. So giving the example of Siang Hwee, these F programs, the concrete execution that let y be 0, and then to execute the program, right? So suppose y is 0, and we were in this example, we can know which statement will be executed based on the value of y, right? So this is concrete execution. And the idea of symbol execution is that we do not want to have a concrete value of y. We want the input of the variable is a symbol instead of a concrete value. So in this case, we will not now y is 0. We will now that y is supposed to be a symbol of A. And all the execution, all the follow-up execution is just based on the input is A. So in this case, we will know that when we input A into, when the input is A, we will know the value of Z will be 2A. Okay, is that understandable? And then we will know that when the Z here is 2A, we can know that if we want to, okay, so, and when we reach this branching statement. So in this case, suppose since we do not know what is the concrete value of A, so in this case, just like Siang Hwee mentioned, we might execute 2 branches because we do not know the concrete value A. So we can either to execute it, let A be, assuming that this condition is satisfied, we can go these branches, and assuming this branch is not satisfied, we will go that branch, right? Suppose here is another value like x equals 3 times z, and the value of x will be 6a, and here another w equals log z, and this w is supposed to be log 2a, right? Something similar like this. Then we come to the questions: what's the benefit to have the input as a symbol? And the ultimate, I think the short answer is that we want to know if we want to satisfy a certain condition in the program, and we can solve the A. For example, if we want to know what assignment for A, so that the program will reach this failure statement, that will be simple because the value of D is 2A, and the equation or the constraint here is 12 equals 12. So in this case, we just need to solve these constraints. So we can conclude that when A is equal to 6, and this statement of failure will be executed, right? So in this case, the idea is actually very fantastic. We have the simple, we let the program execute the simple instead of execute a concrete value. In this case, we can know the constraints, or what constraints to be satisfied to reach certain statement. So in this case, so usually the symbolic execution consists of 2 parts. The first part is called a symbolic execution engine. In this case, the programs where the engine is more like compiler or interpreter, but this interpreter is designed for symbol. It will execute a symbol line by line and to construct the constraints. And those constraints is usually called a pass condition. When we got a pass condition, there's another component called an SMT solver. The SMT solver is a component which will take the input of all the constraints and return what assignment will satisfy the constraints. So in this case, the simple execution can work, but just we discussed, right? Just mentioned by Siang Hwee, since there's a huge number of branch and nested branches or even while loop, so the constraints will be super complicated, and the number of passes will be like an explosion. And also it becomes problematic when we invoke some native library like socket or like the other very fundamental library, which makes the constraints incomplete. In this case, if we feed that incomplete constraint to the SMT solver, the SMT solver will not, even if they will have a correct answer, it may not lead to the final execution of our target statement. And even worse, which is the most important, and which also is the most important problem, is that the modern SMT solver can only solve most linear constraints. That means if we feed a log 2a into the constraints, the SMT solver will return an unknown result. So that's the basic basic reasons why symbol execution is a fantastic idea in academia, but it will be hardly used in industry. Okay.
Okay. Yeah.
Okay. Keep going on.
Okay, sure. So over here, I actually have another code snippet. maybe if you all run through like a symbolic execution, what are the constraints that will actually result in a failure at line 11? Yeah, maybe one of you all can give it a try.
Anyone would like to have a try? Okay, now it's the time for appointment.
Maybe Yucheng maybe. Oh, Yucheng is Xianglin. Yeah.
Let me see. So
Yeah, it might be better to just work backwards to find what are the constraints that need to be satisfied for it to result in failure.
yeah, so from this line to so this bar is 1.
Yes, correct. Actually, can. Actually, the main constraint is line 4 as well. If line 4 doesn't work, then yeah, all of them wouldn't actually constrain. Yeah, regarding 5 and 8, yes, you raise a good point, but there are other factors also that might result in it. Yeah, so the main constraints are actually, if you ask me, is on line 4, line 9, and line 10.
Oh, yeah.
Okay, can. Yeah, okay. Okay.
Okay, so
Okay,
we haven't got the answer, right? We haven't got
correct.
what is constraints to reach the failure.
Yes. Yeah, okay. So now to go down into the shepherded symbolic execution. So for example, let's say we run a program, like we run the full program itself with the input 0, 2, 0, 2. So if you run through the program, actually you'll realize over here x is 2. All of them would satisfy this condition. So if we follow the path that the program takes, line 2 will run, line 3 will run, line 4 will run, line 4 will check, and line 4 will actually branch to line 5 because all of them satisfy this condition. So line 5 will run. At line 6, because v of c is equal to 0, it's initialized to 0. So line 7 will run. And then line 8, line 9 will run, line 10 will run, and this 0202, this input will actually result in a failure. Correct. So because of that, if we run through, we can see that the control flow trace is actually like that. From line 2, so all of this will run at the branch here. At branch 4, it actually goes to line 5, so 2 to 5. And then at this branching statement, line 6, it actually takes branch number 7. Then 8 and 9 will run. At branching statement 9, it actually goes to line number 10. And at branching statement 10, it actually goes to line 11, which is the entire control flow trace. So some of the lines are not important because they are expected to be taken. So they only keep track of the branch that it takes after the if loop. Everyone clear about how this control flow works? Yeah, so this control flow trace is based on the input 0202. Okay, so because we have a control flow trace that actually guarantees us to hit failure, we actually don't need to explore any other path, like from line 4, whether it will go to line 12, or from line 6, or from line 9, it will go to line 12. Actually, all of those paths are really not relevant to us. We are only interested in the path that we take. Granted, there are actually other paths that might still reach failure, but what we know is that this control flow trace will definitely give us a failure scenario. Yeah. So actually, based on this valid failure path, we can actually find the constraints that needs to be satisfied for us to get a failure outcome. So if we look at it, as Xianglin mentioned just now, so one of the first constraint is at line 4. which is that X must be less than 256. And since if we use the symbolic execution, X is actually just a sum of A and B. So we know that A plus B must be less than 256, C must be less than 256, and D must be less than 256. So for the first constraint is that, yeah, A plus B is less than 256, C is less than 256, and D is less than 256. Moving on, we notice that for us to hit line number 7, C cannot be equal to X. Because if C is equal to X, this value is 1 and we will not hit line number 7. So notice that actually whether we go into line 6 or 7 would not really affect whether we hit failure or not. But because we are just trying to follow the same control flow that guarantees us to hit failure, we will have to satisfy this constraint as well. Constraint at line number 6. So for line number 6, C cannot be equal to X. And so it cannot be equal to A plus B. And then moving on, at line number 9, C is less than D, and C is less than D, so there's another constraint that we must satisfy. And the last part for line number 10, we know that because we want this to be equal to X, and only V bracket X is equal to X, so we know that D will be equal to X, and then it's equal to A plus B. So in a sense, we have an entire list of constraints that we need to satisfy to hit the failure situation. So if we simplify this, we actually get something like this. Yeah, so this is not done using any solver or anything. It's just by looking at it. And we notice that actually with this, we can generate any number of test cases. It might not be the same test case, but any of the inputs that satisfy these conditions would ensure that we will get a failure situation. So this is one way of how with the shepherded symbolic execution, we can actually already derive the inputs to the system itself. Any questions?
I think that is fairly clear.
Yeah. Okay. So moving on, but of course, yeah, this is a very simple code and it's a very optimistic method. So in actual fact, okay, so the idea behind it is that it will just keep updating the path constraints until it reaches the failure, or there's actually a symbolic execution store, which happens because our constraint is too complicated, which I will show in the later part. So if either of these two situations occurs, it will, okay, when it first hits failure condition, by failure I mean line 11, it will try to solve the constraint, which is something like this. And if it's able to solve the constraint, it actually will be able to generate the test case. So as I mentioned, the test cases might not have the same input, but it will have the same control flow outcome. This doesn't happen very often. So out of their tests, out of their 13 different experiments, only 2 of them are able to solve it within the first run. If not, it will actually construct a constraint graph. So if it's not able to solve the constraint, or there's a symbolic execution, it will actually construct a constraint graph to be passed to the key data value selection. Yeah. So up to here, is there any questions? Okay, if not, moving on. So regarding the constraint graph construction, so as mentioned, it's constructed when the solver times out, and it actually describes any dependencies between the values and the constraints that we have. So each of a node within the graph represent the operations or constant or program input in a symbolic manner, as well as the objects in symbolic memory model and the symbolic memory address. So a symbolic memory address or the symbolic memory model, if you recall the example previously, we had an array of V. So that is actually, and we actually constantly have to assess the array to update its value. So the example I gave just now is very simplified version of how the constraints can actually be deduced. But in actual fact, something like writing to memory is a lot more complicated than that, because we do not know. This is the X in this case is referring to some part of memory in V. So if we use this same example of the control flow trace being 2, 5, 7, 10, and 11, when we look at line 5, we actually see that the program actually uses the value X, which is A plus B, to dereference the entry and assign a value to it. And this actually creates a symbolic memory address. So what that means is, because we do not know whether, for example, V of X is equal to V of C. So because of that, we actually need to create something known as a symbolic memory address to keep track of it. So even though we cannot determine what's the address of V of X, however, because we know that from line 5, it doesn't just terminate, it shows that this path actually this line does not lead to any failure. Yeah. So because V in this case is updated symbolically, so what we know of V is that it's actually 255 of 0, and there's one entry that is a 1, but we do not know which entry of V is a 1. So because this is all symbolical, so we only know that we can only interpret line number 6 as it being a read of the right of the entire array. So this right Vx1 is the new array where it's 2550 and there's a 1 1 somewhere in the array. So we will read from this array the value at memory C and compare it to see if it's 0. Yeah. Are you clear with this part? So the idea is that because we are using symbolic expressions, we do not know what is the actual memory address, but we know that there is a value within this array that is array returned to be a value of 1. Any questions?
And then what is the symbolic execution constraint look like?
Sorry?
So in this case, if we consider the
Okay,
symbolic
what is
memory,
the constraint, right?
Yeah.
So the constraint is as mentioned, it will look something like this. Because if you notice here, is read write V, the symbolic X is actually symbolic A plus B, 1, and then C must be equal to 0. So it's not as simple as the basic constraints that I have previously. This is a bit more complicated because it actually assesses the memory. Yes, so if we notice, this is just one write operation and one read operation. But if we notice, line 7 itself actually does another writing operation. Yes. So with more and more read and write operation, it actually becomes very complicated.
And then the memory address, then the symbolic memory address becomes very, very uncertain, right?
Yes, it's very uncertain.
And we don't know which element or which address to be 1 and which address to be 512.
Yes, correct.
Everything is possible.
So yeah, to show an example of how complicated it can be. Okay.
And in this case, I think it will be a normal example will be considered complicated in their approach, right?
Yes. So actually
as long as I use an array, for example, if I in Java, so if we use array list, or we use a hash map.
Yes.
Once we're using this data structure, very commonly used data structure, that will be considered complicated.
Yes, correct. So actually, they have in the later part, they actually isolate out what are the reasons for it being complicated, and they actually focus on those areas itself. Because as we know, the main reason why it's complicated is because we are reading and writing to a certain memory address that is uncertain. And actually, assuming if my array is 256 versus if my array is of size 2, the one that is 256 is actually a lot more ambiguous than the one that is of size 2. Yeah, but we will touch on that later during the key data value selection, because that will actually narrow down as to whether what kind of values they are trying to keep track of. Yeah. So we can see how it can actually become very complicated. Yeah. So how the constraint graph would actually be constructed is something like this. So if we look over here line by line, so it starts from line 3. Okay, it first starts off with all the symbolic variables. So lambda A, lambda B, lambda C, and lambda D. These are the symbolic variables that are taken into the function itself. Then from line 3, we know that x is equal to a plus b, so it's an addition. Then from line 4, we know that there's a comparison of these 3 variables. So if we notice just the first one, by right is x less than 256, but x is actually an addition of lambda A and lambda B. So this is how it's represented. Yeah. Then line 5. So line 5 is where the first write to a memory address, to a memory space occurs. So it actually writes to v a value of 1. Okay. And yeah, 1 is a constant in this case. Then the next part is line 6 and line 7. So line 6 is actually this portion over here. It does a read based on the lambda c itself to see if it's equal to 0. Then only when it's equal to 0, then there is this writing of a value of 512 to this v itself. Yeah. Then line 8 and line 10 is also similar. So there's line 8 is actually reading and then writing to this vx, and line 10 as well. Line 10 is reading it twice and doing a comparison. Yeah. So this is a so-called constraint graph that will be created.
Here, so
yeah.
So there's the value dependency, address dependency. Value dependency means that the write need to take the operand, right? Need to take the operand of the result and add. And the address dependency means that
address dependency is because when it needs to get
and can you explain a bit about the write to have address dependency? Have address write to have.
So if we look at line 5 write to, right? So it's writing a value of 1 to the array at position x. So x in this case is the address of the array where it's writing to. So that's why there's an address dependency on x. Is that clear or? So
as long as a write or read.
As long
as a write or read operation is operated on an array or an object. So it will create an address dependency here. So basically, it actually cause a reference here.
It depends. Right. I mean, if I write v0 equal 1, then there will not be an address dependency. Because
it will not address because address is determined. Right? Because address is not symbolic. Right.
If the address is constant, then there will not be an address dependency. But because this is symbolic, it leads to the problem that we face. So if you notice, if I were to chain all of this up together, so if I were to chain it all up together, so line 5 is actually very simple. You write to x that is equal to 1. Then at line 6, it actually writes to this new array. So maybe I'll annotate it. So over here, this part here is actually this one over here, which is this array. So what it's doing is that line 7 is actually writing to this current array at position C a value of 512. Correct? Then if we look at line 8 itself, line 8 is actually immediately it becomes very complicated.
Yes, it's been nested again, right?
Yeah, because it's nested multiple times. So line 8 would look something like that, which is because it actually writes to this array. So this part here is the same array from line 7. But before it can write to this array, it needs to get the position Vx. And for Vx to work, it needs to read the array itself to find the value of x. And yeah, so we can see how from actually it actually scales up very quickly. And this symbolic execution actually becomes very complicated after a while. So actually, yeah, as you mentioned just now, is that a lot of this complexity comes from writing to a memory, because that one is very ambiguous. Yes. Okay, so moving on to key data value selection. So the idea behind key data value selection is that we want to eliminate stores. So stores will occur when our symbolic execution is very complicated. So how it actually eliminates the stores is that it actually analyzes the constraint graph, and then it determines the key data values that will help to simplify the constraint. So for example, if we look at this situation over here, right, we notice that if we just keep track of a few values, we are actually able to get a better idea of the path constraint itself. So if we look at line 8 itself, which is a very complicated line itself, or symbolic memory address, we can see that the main variables that we need to keep track of is x and c. Yeah, x and c. And also, if we look at it from here, it's also Vx. So these are the three data values that are very important. Any questions? Yeah, so the idea behind it is the symbolic memory accumulation actually results in this kind of complexity to happen. Any questions with regards to this?
I have no problem here.
Okay, can. So one obvious way to do it is to record and replay all the inputs, but that leads to a very high overhead, which we are trying to eliminate. So we know that the key contributors to complexity is the reading and writing. So with regards to reading and writing, there are two things that will make it very complicated. One is the length of the symbolic write train itself. So if we recall, line 8 looks something like this. So this actually is very long and complicated symbolic write chain. So this is something that we need to solve before we can move on to the other execution. The second one that is also contributing to the complexity is the size of the accessed symbolic memory itself. So as I mentioned just now, the size of V is also very important, because if I have a V that is of size 2, like an array that's of size 2 versus an array that's of size 256. So because 256 is way larger, there are more locations that can be accessed. So actually it will be more complicated as compared to an array of size 2. Yeah. So in general, in a program that is running, so for example, a program like this, we want to, the parts where it's very expensive are the parts where it's writing to a large memory location. So we know that, for example, in line 3, it's actually just writing to one variable. So this one, the memory size is not a lot. But in line 5 or line 7, you are actually writing to V itself. And so it's actually 256 as compared to writing to one variable itself. Yeah. So these are the two main sources of complexity, which is the length as well as the size of the accessed symbolic memory. Yeah. Okay, so the idea behind it is that we want to exhaustively search the graph itself to identify the longer symbolic write chain as well as the write chain that updates the larger symbolic memory objects. Any questions?
That's
Yeah.
okay.
So yeah. So these two chains can be the same chain. but they can also be different. So as I mentioned just now, maybe I'm constantly writing to one small array, or whether I'm writing to a very large array. So they can be different or they can be the same. But in our example, they are actually the same chain. So which is the line number 8. Yeah. So because of that, using the values that are read or written in these two chains are actually the values that we want to keep track of. So yeah, so this is how they generate what are the key data that should be recorded. So as mentioned previously, the key values that we want to record in this case is C, X, and Vx itself. Okay, yeah, so this will form the set of variables that are being captured. So lambda C being the symbolic value, X as well as V bracket X. Yeah. So notice that we don't need to store all values like lambda A, lambda B, lambda D. So we actually saving on those memory. Yeah. Okay, so the ninth strategy again is to record all the elements in the bottleneck set. But this can actually, the cost of recording it can actually be further reduced if we are able to find elements that we can either record in the earlier steps so that we can generate the elements later, or elements that are that sort of are not really needed in the bottleneck set. So to explain that, there will be an example further down. So how they calculate the cost in this case is the size of the element, because that is how much space is required to store the element. Yeah. By right, if we come of it in terms of a C perspective, each of these elements, X, VC, and V bracket X are integers. So they have a size of 4 bytes. And then the count is how often they occur in the code itself. So the current cost of this data set is 4 plus 4 plus 4, because each of them only occur once, and then they each have a size of 4, giving us 12 bytes needed to record all these elements. Okay. However, to reduce the size of this bottleneck set, what we can do is we can actually perform a DFS to find if we can record any nodes with lower cost than its current cost. So using the same set as an example, the current set that we have is X, lambda C, and Vx. So if we look at X can actually be represented in lambda A and lambda B. But then because if we are to record lambda A and lambda B, the cost of recording lambda A and lambda B is 8. But the current cost of recording lambda X is 4. So we will choose to record lambda X itself. Yeah. Then lambda C is an input, so there's no other way to find any nodes to give us lambda C. And then for V bracket X, it can actually be determined given X and lambda C. So actually there is no reason for us to record V bracket X. So because of that, our new bottleneck set is X lambda C, giving us a cost of 8. Yeah. Any questions here? Yeah, okay, so this is how they determine what are the key data values to be recorded. So after that, they will just instruct the runtime to record elements of E. So
but for real application, I think there's no need to further reduce
correct,
A and B into X.
Yeah,
right?
so by right, it's just recording the input. Is that what you are saying? Right.
Okay.
Yeah. So yeah, actually, if we record the input, yeah, but because I think this example that you gave is simple enough. So by right, it will make more sense to just record A, B, C, and D. But I think they just want to show how it can actually cut down on the cost.
And also, I'm not sure whether the paper has mentioned this. So, and how about, and here in your example, there has a 2-dimensional array there.
It's a 1-dimensional array.
All right, right. So that's
Yeah,
one dimension
one
already
dimensional.
there.
Yes.
Yeah, and also, have they talked about an object? For example, object could be a graph, have a graph structure, right?
Yeah, correct.
So the graph structure, and there's supposed to be suppose it's a binary tree. So that's one of the simplest structures. And for binary trees, sometimes if we want to reach certain branches, we need to make sure that a certain children or the descendant children will have specific values, right? So have they considered to maintain such a structure information?
Structure information.
Yeah, the structure information. So for example, when they want to record it, the trace, right? So
Yes.
and here there's intermediate variables. For example, this x per se is integer, that's okay. But what if the x is a hash map? And inside the hash map, it will actually make the map to put a equals 1 and map the key to be equal 2. So they have the internal structure inside the program. And if they want to record that, so and that might be some internal structure to be recorded as well, right?
Yes. So in terms of recording that, I think they did not mention it, but I think it will go down to the cost itself. So the cost of the object, because if we look at it in terms of bytes, then
no, definitely if we introduce the hash map and read and write,
oh yeah,
that will definitely increase the
cost of it.
Of the symbolic expression. So in this case, we're choosing x as the recorded variable. And in this case, x itself is actually a hash map, right?
Yeah.
It is a hash map, and how they recorded such a complicated structure.
I think they did not mention it in the paper for like the objects itself. Yeah, because they are trying to they are trying to present their
I think this is actually a very, very interesting topic to me. And also, I think you can also pay attention. For now, we are working on the pure recorder and playing systems, and that will be introduced or Inca runtime overhead. And of course, we introduced a bug there, so it was just making 50 to 100 slowdown of the execution. But when we fixed it, it still have 5 to 10 times slowdown for that. Especially we want to record the variables. So sometimes if you look into the regression or the implementation, both microbit and the regressions, we really have, especially we also need to handle the structure information of variable. So that means the variable has the children have also children, the children have a reference, right? So unless we record all of them, if we do not have that information, the debug becomes harder. In this case, I'm thinking about how to record less information, and when we use it, some information is deducible. We just recover it instead of restore everything. So that is an interesting topic. But I think that this kind of the simplified stuff.
Yeah.
And let me think about a more practical application of this idea. Okay, please go on.
Yeah. Okay. Actually, so with that, with this instruction to record the two elements, so actually it just goes back to this program flow, and then it will run again, but with the variables inside this time. Yeah, and then it will repeat this symbolic execution, and then it's able to generate the test case. Yeah, so this is just how the different components tie up together to work to generate a test case.
I think one of the contributions we can make, we can build upon on this technique. Ideally, I think we just need to run the trace for once.
Yes.
And we can record it what is the key value selection. So that is, but of course we need to do some preliminary or some pre-analysis, like static analysis, to find out what variables are deducible. So we can just we can remove the deducible or deducible variable values, so that we can further so that we can save the runtime overhead. Okay, please go on.
Yeah. Okay. The rest. Yeah. In terms of concurrency, even though it's not the focus of their paper, but what they did is that they actually use a timer to track the execution of the shared memory accesses. Yeah. So then they will record the partial ordering of the instructions across multiple tracks. So based on the timer itself. Yeah. So if the granularity of the timer is fine enough to capture all the data, the memory access, then they are able to reconstruct it reliably. Otherwise, they have to use a state space exploration technique. Yeah, which is.
I think
not
for
practical.
this kind of research, they
Yeah.
have plenty of work on that. So basically, they just record the log and the thread scheduling relevant instructions. As long as they can keep track of which thread executed first and which thread will be executed second, and they basically can reconstruct the idea.
Yes.
They can reconstruct trace. So they keep going.
Correct. Yeah. So after that is actually just their experiment. So what they did is they evaluated it on 13 different failures. These are the failures. There are different kinds of bugs here, like integer bugs or heap buffer overflow, that kind of thing. Yeah, and then they compare the time taken as well as the accuracy against REPT and Mozilla RR. RR being the record and replace system by Mozilla. Yeah. So in general, in terms of effectiveness and accuracy, because REPT is closed source, they actually did not compare with it directly. What they did is they just compare with the results that were published in the paper. So their current model ER is able to actually go down to like 36 million instruction example and still identify the bug correctly. Yeah. On the other hand, REPT, the max it can go to, I think, is about 100K lines of instructions. So with that, it shows ER is a lot more, it's able to handle longer and more complex code base. Yeah. Then accuracy wise, it's able to reconstruct 100% of the control flow. And for REPT, there is a question mark here because due to the limit of 100K instructions, actually some of the failures actually happen after the 100K itself. So it's not a fair comparison in that sense. Yeah. Then to show the effectiveness of the key data value selection. So with key data value selection, 100% of the time they are able to reconstruct the failure. But if they use a random data selection, it's about 7.69% of the time. Yeah. So by that, and to see how the data value recording, the key data value recording helps is the graph over here. So if we look at the number of instructions, if we look at the number of time taken for the same number of instructions, we can see that with more data values, with more data values, it's able to get the error faster, which makes sense. Then after that, when they compare against the Mozilla R&R, overall they perform way faster. The overhead is actually quite minimal as compared to the Mozilla R&R. Yeah. And actually, that's it for their model. So I think the main takeaway is that the shepherded symbolic execution, this is something that I think is very new, but I mean, as Dr. Ling mentioned, it's good in theory, but it might not be good for practical cases. Yeah, but it can help to prevent path explosion. So
actually in this application, there's no path explosion problems, right? So basically they just wanted. So basically the symbol introduced here just for generalizations, but it's not clear to me that why we need generalization. So basically, from my point of view, I think recording a set of the key values is just enough. Basically, it's just enough. For example, and here there's a forced execution. There might be a technique called a forced execution. So the forced execution is that when the program is executed, we instrument the program to force some program to execute the certain branch,
way.
no matter its expression it is.
Oh,
So
okay.
basically, as long as we can record the values, and we just need to force the program to execute certain branches.
Yeah.
Okay, let me think
Okay.
about this. This
yeah.
topic. I think sometimes I just feel a little bit that this approach is a little bit unnecessarily complicated because the simple execution actually takes time. The value deduction takes time. So I think, and also it need to run the program for several times. And it's also unclear to me whether the program is not deterministic because the program scale is it only evaluate their programs on certain programs.
Yes.
And I think my gut feeling is that it's possible that we can just run it for one time, and then we record some key values. We just can replicate it. Maybe it have a larger runtime overhead, but a little bit larger runtime overhead doesn't matter, right?
Yeah, but we might save on the number of times to run the number of iterations. So there's a balance between the two. Yeah. Correct. Yeah. Okay. That's it for this presentation. Okay. Thank you.
Thanks, Siang Hwee. Very excellent presentations. So next one.
I have a question actually.
Okay.
Can you go back to the overhead graph?
Oh, okay, sure.
So if I'm not wrong, how do they calculate this overhead?
How did they calculate the overhead? I think it's in terms of the memory overhead.
The memory.
Oh, memory overhead. Okay.
Yeah. Okay. Can.
Okay. I was thinking that if it's runtime, then how is it possible that multiple?
Oh yeah, correct. It's a memory overhead. Yeah, because the efficiency wise. Yeah. Okay. Can. Thank you.
Okay. Thanks, Siang Hwee. So next, how about Xianglin?
Okay.
Xianglin, wait me for 1 minute. I think I need to open some stuff. Okay, you can maybe first share the slides and have the discussion a bit fun. For 1 minute, I'll be back. Okay, Xiang, please start.
So the paper is called SliceLine, Fast Linear Algebra-based Slice Finding for Machine Learning Model Debugging, and it is published in SIGMOD 2021. So it has two authors. I didn't find much information about the first author, but I guess she's from Russia, and most of her homepage are not in English, so I don't know.
Okay, that's okay.
So the background for model debugging is the training process for model should first have the data collection and validation step, and then you train your model and then evaluate. But the problem is if your training accuracy reaches, for example here, 85%, we still don't know whether it is a good thing. Here, for example, if the data contains some errors, some human errors or measurement errors, or the model is overfitting, or it contains some, or the data have some out of distribution data, and maybe it has some systematic bias or missing fairness. These problems are silent, but they will cause severe problems. So the basic techniques for model debugging is first, some traditional technique is to use cross-validation to sort the loss or even accuracy monitoring. And recently in computer vision research area, we see some saliency maps, which means use a heat map to show which part of the image contributes most for the final prediction, or the occlusion-based explanations. One example is the integrated gradients. I've reported before, so if you are interested, you can check that. But for structured data, which means each of the feature of your input has some meaning. There are two baselines. One is called explanation tables, and the other one is called slice finder. The slice finder is the inspiration of this paper. So it aims to find the top K words data slice. Yeah, later we will talk about what is data slice. Yeah, so that's the background. So here we can first introduce the slice finding problem. We have some notations in this paper. First, X represents data, which is a n times m matrix. It means it has n data points, and each data point has m features, represented by f1, f2 to fm. And each of the input feature, fj, has a domain from 1 to dj, so they are all integers. In practice, if the input features are already integer values, then that's okay. And if it's a float value, then that would binning the continuous features, which means you map the float value to some integer. And if it is a categorical features, they would just hash the categorical features. For example, in CIFAR10 dataset, they would just map the categorical features into one integer. And then the L means one hot encoding. For example, here we have a toy example. It has two. You can first we can look at this part. So it has two columns. Each column represents one features. And for the first feature, it has the domain is 2, and in the second column, the domain is 3, which means it has 3 choices, 1, 2, and 3. And the one hot encoding just map this integer value into one hot vector into this form. So on the left, the red columns represent the first feature, and the black one represents the second feature. And then we have y, which is the prediction. It is a n by 1 vector. We also have one error vector. And for the classification problem, the
sorry, so for the one hot encoders, for one samples, how many columns will be used to represent it? It will be.
You don't know. It based on your input. It is based on your input.
And why we need to convert such n times 1 dimension into the n times n dimension representations?
It is for because in their paper, they try to implement all their features in a vectorized linear algebra operation. So they need to map those features into this one hot encoding.
And suppose their dimension have 1,000 or 1 million. It will introduce a 1 million column there.
Yes, yes.
Okay, keep going.
I have a question. So in the example here, the m of the x is 2, right? Okay.
Yeah. And we are talking about the error. So for classification or regression.
You mean, Changshen, your question is for m of x.
Yeah.
The number of integer features. I think the features are supposed to be 7, right? There have for each x they have 7 features, and for each features they have 2 choices or 2 options. So the dimension for each sample, or for one sample like x, is 7 times 2, and for another sample it will be 7 times 3. Right? So the red part is one sample, and blue, the black part is another sample, right?
So we got.
This is one sample, right? This is one sample.
No. The row, each row represent one.
So we got F1, F2 to F5 in this example.
What do you mean?
So the pink one is F1, or just the first row is F1?
The first column is.
The first column.
Yeah, the first column. This is F1 and this is F2.
Okay. So M equals 2 in this example, yes, instead of 5. Oh, okay.
Yeah.
Okay, so each row is a sample, right?
Yes.
Each row is sample. So one row. Okay, so just expand the dimension. Okay, I think I.
Yeah. So on the left, this part is just one encoding form. They are the same. So the input is this 7 by 2 matrix, but later they will convert it into this 7 by 5. Yeah. I will kind of just answer the questions in this.
Okay, so the idea 1 or 2 is just means the category, right?
Yes.
It's just category. So for example, the category of cat, trunk, and dog. So it makes no sense to say that cat and dog is the cat is one for example, I'm not sure whether I interpreted correctly. So suppose the cat corresponding to 1, and the trunk corresponding to 2, and the dog corresponding to 3. If we just using 1, 2, 3 for the category, so it means that the cat and trunk would be more similar than cat and dog, right? So in this case, we have to using one hot vectors to translate it to 1, 0, 0, 0, 1, 2, and 0, 0, 1.
I think the one hot encoding is for easier calculation.
For easier calculation, what do you mean by calculation? Suppose the value itself is for the number of students. For example, one feature is called the score, right? Suppose one feature is score. The score is ranking from 1 to 100. In this case, we do not need to bother using one hot vector to encoding the score. Do we? So suppose that we're using one hot vector, which means that suppose the one gets, suppose someone get a one score of 1, and someone get a score of 2, and then someone get a score of 2. So 3. In this case, if we use one hot vector, it will be 1, 0, 0, and the 0, 1, 0, and the 0, 1, 1. Suppose be something like this, right? So in this case, it means that 1 will have a larger distance with 2, while 2 and 3 have larger distance than 1 and 2.
I don't think in this paper they care about the similarity here. When I say that it's for easier calculation, I mean, for example, in the first for the first feature, the red part, right? When they try to calculate how many rows that have the first feature to be 2, they can just calculate the sum of the second column.
Just for efficiency.
Yes, yes.
If that is for efficiency, that is for a database or storage concern. But from the machine learning perspective, it doesn't care about whether we store it with 112 or 101001.
Yeah. Yeah.
Okay.
Because it's not.
I think that would be only applicable for categorical feature, right? If it's not a categorical.
Yeah, so that's why this paper is based on the structured data.
Based on the structured data, maybe you can keep going on. So, but anyway, so the approach here is very clear. So for features with value range between 1 and dj, when the d and it's supposed to be turned into a one hot vectors with d dimension, right?
Yeah, so the first question, what is the value m in this example? So the m equals to 2 and n equals to 7. And D1, maybe Changsheng, can you say what's the value of D1 and D2? So D1 is the domain of the first feature. How many choices do this feature have?
D1, let me see. What's the definition of D? Has a domain 1, 2, 3.
So how many different values of the first feature?
2.
Yeah, yeah.
And D2 is 3.
Yeah, yeah.
And one hot including is the sum of all the D's as 5.
Yes, yeah, that's correct. Yeah, thank you. And then the predicate means you find a value v from feature fj, and v should be inside the domain of dj. for example, here we have one predicate, F2 equals to 3. This is called one predicate. And again, here's a question: how many rows will be selected if we have this predicate?
It's time for appointment. It's time for appointment.
Yeah. Maybe Yufan.
3. Is it 3? How many rows will be
selected if 3?
F2 equals to 3. That means the second. Let me check. F2 equal to 3. How many rows will be? How many rows will be?
Because each row represents one data point, and
sorry, I didn't know, because I think maybe
it means the F2 equals to 3 means the second feature is 3. It's like a database query, right?
The second feature, the V belongs
the second column.
How many 3 are there in the second feature?
Yeah.
Oh, okay. 1, 2, 3, 4, 4.
Yeah.
Okay.
Yeah, that's correct.
I got it.
And then further, we can define the data slice. So the data slice means 1 to m equivalent predicate, and we have one condition is that there must be at most one predicate per feature. And then there are some other notations in this paper. The S means the slice size, which is the number of rows selected. Yeah, just as the example, if we have predicate F2 equals to 3, then this slice size should be 4. And then L is the size of one hot encoding, which is the sum from D1 to DM. And then the ES represents the row aligned arrow vector, which has a shape of S by 1.
What do you mean by arrow vector?
That means the arrow for each of the data points in your slice. For example, if here we have selected the slice for F2 equals to 3, then we have the first, second, third, and the 7th rows. And the ES has a shape of 4 by 1, and each represents the arrow for the row, for each row.
Assuming that, so the hit arrow means that suppose given a slice, in this slice, this data slice, including a lot of the prediction error or the deep learning prediction errors, and we will consider such a slice.
So each data point has, this is E1, E2, right?
Each data point is an arrow.
Yeah, has an arrow.
Each data point has an arrow. So what do you mean by each data point has an arrow?
Like here we have a definition. If for the classification problem, if the prediction of this row didn't match the label, then
it is
E is 1, otherwise it's 0. And for regression, it's the difference between the true label and the prediction. So each data point should have one arrow value.
Okay.
Yeah, and then the E bar is the average value for the whole data set. And then the slice error, SE represents the total error for one slice. And then the SM represents the maximum slice.
Sorry. So I somehow slipped it. So the slice error. So how do you define slice error? The sum of
all the error in a slice.
Okay.
And then the SM.
And the ES is still a slice, right? Yes. So consider slice in the set.
ES is a vector.
Oh, ES is a vector. And the vector corresponding to
the slice you select.
Okay.
And
the slide, the given slice, and there's the error vector. Okay. So what I call it ES, error slice. Error slice. Okay.
And then SE is slice error, and SM is the maximum slice error. So you just select the maximum from the ES. And then SE bar is the average slice error. Yeah, they have a lot of notations in a paper.
Okay. I think I cannot memorize all of them, but you can.
Yeah,
I will keep asking.
Yeah. And then, for generally speaking, the slice finding problem is to find sufficiently large slice with substantial errors. So you find a subset of your data that have a total error that is above the average error of your whole data set. And
so basically it's optimization problem, right? So as long as we got it, so basically we want to find a slice. Basically slice is just a query, right? So we just want to find a query. In this query, inside the query, when giving such a query and the number of error inside such a result returned from the query will be as high as possible.
Yeah,
so that is basically such a formulation problem.
Yes. Okay. And then, but here we have a trade-off. First, the slice size should be large enough. Otherwise, you are just choosing some outliers from your data set. But at the same time, the total slice error should be large as well. So there should be a balance between those two measurements.
So here, maybe I ask another questions. So of course, if for the medical recall, definitely we can use this approach. And how about the image or the natural language? So basically, it is not that easy to define such a slice, right?
Yes.
So the pixel is actually one dimension, and it's ranged between 0 to 255. And if we pick up slice for that, one pixel actually means nothing.
Yeah. So this paper is based on structured data. Each feature in the data has some meaning. For example, if you have a data set adults, then the features might be his age,
nationality, age, gender, etc. Okay, so basically, it's also that's why they're looking to the categorical feature.
Yes. Yeah.
So basically, we can still do something like deep learning, right? The deep learning. So of course, the pixel level is definitely not applicable. But if we go to the gap layer, then it becomes applicable because each dimension corresponding to certain category, maybe whether giving the human face means eye, nose, mouth, ear, etc. Okay, keep going.
Yeah, I think so as well. But first, we have a motivating example here. For the slice finding problem, suppose we have a very simple data set with m equals to 4 unary features. So here in the graph, each node represents a combination of predicates. So in total, if we try to search the top k data slice, then we need to search for every node, and that's 16 nodes in total. And then to make it more general, if we have just m unary features, how many nodes should we search?
It's a question?
Yeah, it's a question.
Okay. So this is another time for appointment.
Let me see. Darian?
Yeah.
Yeah. Hello.
It's just a combination of problems.
Oh, yeah.
And each feature have two options, right?
Yes.
And we have n features. And how many options do we have? That's a basic idea. That is just basic idea.
And we'll have 2 to the n possible options.
Yeah. So yeah, that's correct. The answer is 2 to the power of m. And that's the case when each of the features has two choices. And if each of the feature has multiple choices, then the complexity would grow even more. So to search every node inside this graph is not applicable. So the key idea, I think the key idea in this paper is how to prune some nodes so that the search space can be minimized. And then for the SliceLine, it refines the problem as the constraint scored based top K search. Here we can first look at the score function they define. So remember in a previous slice, we say about a trade-off between slice error and slice size. We hope that the size can be large enough, but the error, the slice error should be also large as well. Yeah, so I think that's basically the idea of this function. The alpha is a hyperparameter to balance between slice error and slice size. And the slice error is defined as the SE bar divided by E bar. The E bar is the average value, average error for the whole data set. And the SE bar is the average error for the slice, for the slice. So if it's larger than 1, then that means the slice error is above the average error. And then for the slice size, it's n divided by s. So the size of the whole data set divided by the size of the slice. And we hope it to be large as well. And the second line is just an expansion to the first line. The SE bar is the total slice error divided by slice size. And then this part is the average error for the whole data set. And then some interesting properties about this score function is, first, if alpha equals to 0.5, then that means a slice with twice the relative error, but half the size of not another slice, but half the size of the whole data set has the exact same score. And then the score of the original data set is 0, which is independent of the hyperparameter alpha. And the third property is that when alpha equals to 0, which means we entirely focus on the size, then the maximum of the score is reached when we select the whole data set. And the last feature is they mentioned that the function only relies on size and errors, which is easier to compute. So that's the score.
Oh wait, so here, so if the size of the if the slice size is the half of the data set, so the right part 2, right? So 2 minus 1 is 1. And with twice the error.
Relative error, which means the SE bar divided by E bar is 2.
Okay, so I just wonder why it's not normalized. I was just thinking.
Which part? You mean?
I mean the optimization loss, the tree optimized loss. So it's not normalized, right? So it can be very, very large.
You mean SC?
Yeah, SC. Okay, that's okay. Let's keep going on.
Okay. And then they can fully define the score-based slice finding problem. So here the input is X, which represents the data. E is the error vector of the whole data set, and K is the hyperparameter. Means how many slices would you like to choose, and then they hope to find the top K slice, which can maximize the score function, but with 2 conditions. One is the slice size should be larger than sigma. The sigma is also a hyperparameter. And then the slice score should be larger than 0.
What does larger than 0 mean?
The score should be larger than 0.
And I think SC include the size of the slice. Can you go back to those SC? So SC actually including the slice size already, right?
Yeah. So the first half is about the slice error, and the second half is about
So why we still need to consider slice size again? Or it's always just a threshold. We want to make sure the slice size is always larger than the sigma. Then we consider the balance. Okay. Okay, larger than 0 means. What does this larger than 0 mean? Being larger than 0.
Also a threshold, I guess.
Okay, maybe it cannot be too small, right? Okay. Okay, but why 0, not a row? Another threshold, maybe alpha or.
The third feature is when alpha equals to 0, then I'm not sure. I think it's just a threshold, I guess.
And why to be 0? Why should be 0, not -1, or not 1, or not 0.5?
I don't know.
Okay, keep going on.
So they just changed the pruning process into this score-based slice finding problem. And then we can still look at some basic properties for pruning. As we mentioned before, if each of the feature has two choices, then the search space should be 2 to the power of m. And inside this toy example, we arrange it to have m plus 1 levels. And here is another questions. A node in level I has how many parents and how many children? And maybe Ruofan.
parents.
Yeah.
Mm.
Because
I'm -1 children.
-1.
-1.
So the answer is I parents, that's correct. But for the children it's m minus I.
Oh, I'm minus.
Yeah.
Oh.
Yeah. And then there's some monotonicity as the path goes deeper, which means the slice size would decrease. So I think that's easy to understand because if you add more predicates, then the row selected would be less. And then the slice size should also be less than the minimum size of all its parents' slice. Right.
The minimum size. So the parent size is both parent. The parent should have the same size. Oh, not necessary.
That's
Oh,
for example, it's the parents and this is the current one, right? Because you add more predicates here, then.
Definitely, yeah, you're right.
Yeah, and then the second property is the absolute slice error would decrease. Yeah, because the row you selected decreased, then the error should be less as well. And then it should be upper bounded by two different conditions. The first one is the total error of a slice should be less than the minimum parent slice. Yeah. And the second property is it should be less than S is the minimum slice size of all its parents, and then times the minimum maximum parent size. Oh, that means for the current predicates, the maximum size is the minimum parent size, right? And then it times the suppose it has some parents and
SN is parent.
They are parents. Suppose we have P parents, then the last one is SMP. The SM means the maximum error in the parent slice. And then from all of them, we select the minimum.
Given a slice, given a slice, didn't the error size will be fixed?
Yes, but here we are trying to find an upper bound.
Yeah, so basically we just wanted the minimum size of the SM. Right, the minimum error size of SMI.
The minimum, yeah, because the minimum of parent slice size is the maximum for the current node.
Yeah.
And then we find the minimum SMI.
Yes.
And times the size, it should be the upper bound of the current node.
As the size is the size of current slice.
The size is the
total size, the total state size.
Not the minimum parent slice size. And then times the minimum SM.
The minimum. So what do you mean by the minimum parent?
The SMI represents the maximum value in the parent slice.
But given parent, its error size is fixed. Why we still care about the minimum? Why there's a minimum or maximum?
What do you mean by fixed?
So given a slice, this slice could be a parent, right? So given, so what do you mean by the minimum error size of a parent slice?
That means we don't look at the current node. We look at all the parents node.
So here, let me. So this is a slice, okay? This slice, and it has two parents, okay? A and B.
Yeah.
That's fine, right? So given a parent A, given a parent slice A, its error size is fixed, right? So let's call it AN, okay? And here is BN, right? But anyways, the upper bound of the slice of AB is the minimum size of AN and BN, right?
Yeah.
Right. So here, what do you mean? What's your explanation? What do you mean by the minimum size of one parent size? One parent slice?
I mean, let's say the S is the size we found, the minimum parent slice size, and then it should be it should times a upper bound error. What's the
hello?
Yeah, so the maximum error for AB should be the minimum should be.
Yeah, that's okay. So the minimum is supposed to be S here, right? The minimum is SU right here.
No, S is the size. We are trying to find the maximum error for AB.
Yeah, so okay. So I'm asking now my follow-up question that S is the size of what?
S is the
size of data size, the data set, or
the minimum slice size of AB.
The minimum size of slice, the minimum size of slice AB, but giving the slice of AB, its size should be fixed. Am I right?
I mean AB's size.
Yeah, the size of AB should be fixed because we already decide A and B.
Yeah,
the size is, so what do you mean that the minimum size of the slice AB?
That means when we are given the parent nodes of one current node, we don't look at the current node. We found the upper bound by looking at all its parents.
So okay, so there are several concepts. The first is the slice size, right? The second is about the slice error. So we haven't touched about the concept of slice error. We just talk about the slice size. Am I right?
Yeah.
So when we talk about the slice size, so basically it's quite understandable that given the slice, and its size should be bounded by the minimum of the minimum size of its parents, right? So basically we just need to suppose, I'm not sure what your symbol S means, but definitely it will be actually, if I'm going to write the equation, the minimum size parent, right?
Yes. Yeah,
so,
that's
okay.
S.
Okay, so that's S. So And then you mentioned there's still a factor should be multiplied with it. And what's that?
That's the, because we are finding the total slice error for AB, right?
Total slice error. So okay, so the size, we have finished the discussion of size. Now we're talking about error.
Yeah.
Right.
Now,
okay.
next we should find the max error for AB, right? Then the max error for AB should be the minimum of all the maximum error for its parents. So SM is the maximum. Let's say SM is the maximum error for the first parents, and then the second parents, the maximum error for second parents is SM.
Okay, so let me interrupt again. So the error size for a slice shouldn't be fixed. It should be fixed, right? So the error, the error size of A is fixed. So what do you mean by the maximum error size of a parent slice?
I mean, for P1 we have a maximum error, right? For P2 we have a maximum error SM2.
Maximum, but it should be decided, right? So the size should be decided. So is that assuming that so here the question that given a parent slice, is his error size be fixed or not?
Yes.
It's be fixed, right?
Yeah.
So there's only one error size for one parent slice.
Yeah.
Right. So what do you mean by the maximum error size of the parent slice?
The maximum error. Then to make it simple, the maximum error is a value. Right.
So when you talk about a maximum, it means that they have multiple error size of a parent, right?
The parents, depending on the size of the. Remember that we have a error vector for each slice.
Yes.
And then we find the maximum error.
So given an error vector, there's supposed giving an error vector, there's supposed to be one error size because the error size is the sum of the error vector. Right.
Now
so that means so that means given a parent slice, it will have a fixed error size.
Yes.
So we
are finding the maximum error value from that error vector.
Okay, so only one data point, right? So that maximum error is for one observation from the slice.
Yes.
Yeah. Oh, okay. I think I get it.
So can you? I didn't get it. So can you be more specific?
Because for a slice, it has many observations, right? Then you just find the observation with the maximum error. That is your SM.
Why a slice has many observations?
Oh, because one slice you are slicing in your data pool, right? So one slice results in some subset of observations.
Yeah.
Which satisfy the predict.
Yes, but one slice have a fixed set of the observations, right?
Yeah. Then you just calculate the error vector for all those observations and pick the maximum one.
Yeah.
The maximum is the SM.
So Xianglin, would be back to the previous slides. Maybe I missed the concept. So once we have the slides, so we keep the notation here. Let's go back to the previous slide. And the previous one. And the previous one.
This one.
Yeah. So here, so once we have slides, for example, you say given slides, let the second features equals 3, right? So Ruofan, what do you mean by there's multiple observations and we have the maximum value?
Oh, for example, if you choose all the data points which satisfy F2 equal to 3, then you are actually choosing 4 observations, right?
Yeah.
Sorry. Again.
if you are choosing the slice which satisfy f2 equal to 3, then you are having 4 observations, right?
Yes, we have 4. So your one observation means one sample.
Yeah, one sample.
Okay. So we have 4 samples. Okay.
Each sample has a prediction error, right?
Yes.
Then you just pick the observation with the maximum prediction error, and that maximum error is SM.
But isn't the prediction be fixed? For example, suppose we have sliced these four samples, right?
Yeah, it's fixed.
And it's fixed, and isn't their prediction be fixed?
Yes.
Yeah, it's fixed.
And here, suppose the first one is for error, and true, right? So we will get the error size to 3, right?
No, we are not
Well,
talking about
we're
size.
picking the maximum, right?
Yeah.
Maximum value out of this 4.
Yeah.
So you're only left with 1 value.
I didn't and my problem. So what do you mean by maximum?
Oh, okay.
From my point of view, the number of 3 is fixed.
If this is wrong, then it is actually 0, right? The error is 1. The error is 1. If it is right, then the error is 0. So you just compute what is the maximum. The maximum is 1. So this is SM.
Oh, so it's not so here. So the maximum is okay. You're not talking about the slice. You're talking about one observation. So the maximum means the maximum actually means
also associated with the slice you have, because you are taking the maximum from the slice. So yeah.
So the maximum, so the maximum is not for the slice. The maximum is for the samples in the slice.
Yeah.
Okay.
Because
so here the problem, there's the problem of explanation, the concepts here. Okay, you can. So here, so the maximum slice, the SM is actually is pointing to one specific or one individual error, right? Okay.
The high level idea to find the upper bound of the total value of a slice is you find an upper bound of the size, and then you find the upper bound of the error, and then you times the
together. So that's yeah, you're right. That's upper bound. Okay, keep it going.
So the minimum, you find the minimum among all the SMI, and that's the upper bound of the error for, let's say, for AC.
Okay.
Because we found those 2 upper bounds, then the total, the final upper bound for SE is the minimum of those 2 parts.
Okay.
And then for the last part, inside this function, the relative slice error the relative slice error should be SE bar divided by E bar, and it's not monotonic, because as the path goes deeper, then the size decreases. The SE decreases as well, so we don't know the upper bound for relative slice error. So to fix this problem, we just talked about them. So to find the upper bound for the relative slice error, we replace the SE with the upper bound of SE, and then from all the size between sigma to upper bound S, and then we calculate the maximum value, and that's the upper bound for score function.
Okay, so I'm interested about algorithms, and based on the properties and how the algorithm will work.
And then for the pruning technique, So first, it should be really easy to eliminate a node and all its children with S less than sigma.
Yeah, the first two is straightforward.
And then also they need to handle all the prompt size slices, which means when calculating when dealing with current nodes, they need to remember the prompt parents node and remember to discard them. So anyway, the summary of those pruning technique is with the levels go deeper, the slices size should decrease, and then the errors would decrease. The lower bound of the score should increase, and the parents node would increase as well.
Okay, keep going.
Oh, sorry. And then this is the algorithm. So first, they would do a data prepare to turn the input feature matrix into one hot encoding form X. And then initialize all the parameters with one empty node. So they calculate the average error, the all the slices, the statistics, which means the SE, SM, SS, and SC we mentioned before, and CI is the row index of each slices, and later they would return the TS, which is the top K slices, and TP is the scores for the top K slices, and that's the initialization. And later they would enumerate level by level. So first they would do a pair construction, which means to here, for example, in the level 2, then AB would be constructed by pair A and B, and AC would be constructed by pairing A and C. And yeah, after the pair, they would apply all the pruning techniques based on what we just discussed. And later, they would also do a pair deduplication. That means AC and BC, or AB and BC, or AC and AB would all construct one shared node ABC. And in practice, they need to do this deduplication and make sure we only have one ABC.
Okay.
Yeah, and then the fourth step is the slice evaluation, which means to evaluate the scores of all candidate slice and then remove those slices that has a score that's less than the upper bound of the score is less than 0. And then again to output the statistics and the top the statistics of all the slices, and later to do a maintain top K operation.
The keep search.
Yeah.
So is there a budget for a search?
They would do this until I guess you should input a level, an upper bound of level L, or they just keep going. And I do omit some details because I think they spend a considerable part to explain how to implement those operations with pure vectorized linear algebra operations to speed up. So I think there are 2 details. So
yeah, let's keep going.
Yeah, so yeah, that's basically all for this paper. And in the experiment part, they evaluate first the pruning effectiveness, and then the top K characteristics. The third one is the end-to-end efficiency, and the fourth one is the scalability of SliceLine. As you mentioned before, if the rows or the columns becomes too large, that's the problem. And first, the environment.
So, yeah, I understand those is a hardware environment. So, what kind of data set are they using?
So they are all structured data with
the structured data means the table data, right?
The n rows is the number of data points or observations, and the columns, the m means how many features do this data set have, and L is how many dimensions after they converted the input into one hot encoding form. And the last
encoding form is basically for efficiency calculation. Right. So just based on the lattice structure, I didn't see the necessity to put the one hot encoding.
Yeah, they are in the details of those.
Okay, so that's why it's a SIGMOD conference paper. Okay, keep going on.
And first is they do a ablation study in a simple data set. This salary data set with only 397 rows and 5 features. And
by the way, have they open sourced their code?
I didn't check.
Didn't check, right? So here, I think for our approach, we're not the one who investigating the technical details. For example, building up the lattice and do the pruning. So there is definitely very smart and intelligent ideas to optimize the search algorithms. But I think maybe if I'm the one who do this, but of course it's great to have some theory there. But if we are the one who implement these, maybe we can define some optimization algorithms and let it search. So that is another way to do this. I'm sort of is that if their source is open, maybe for the data analyzing, because anyway you are working on the data visualization, right? We want to see, basically we want to see what kind of data, or anyway the cat and dog will have the most errors. What class will have the most errors? But this is what visualization can do. But if we go into the intermediate gap layers and if we apply this approach, of course, we also need to know what each dimension in the gap layer represent. If we have these ideas, maybe we can have the explanations for that. I don't know. Let's keep going on. And it's good to know that they have a technique can find the most error-prone categories, or what is most error-prone slice, the data slice here, right? But what to do next is a little bit, it's still an open question, right? Okay, let's keep going. Let's finish this work as soon as quickly, because technical details is not our concern. Our concern is that they are the infrastructure for us to use, and we need to think about. Suppose we have already known, given a slice, it is most error prone, and what should we do next? Okay.
Yeah. So the ablation study first, they compare whether they have no parent handling and no score pruning and even no size pruning. What's the difference? And the blue one performs the best, and if they have no deduplicate operation and no parents score size pruning, then the memory it ran out of memory at level 4.
Okay.
Yeah, and Yeah, and then they also evaluate different data sets, but I'm not sure why they say that the evaluate slices and match the size of valid slice still exceeding sigma is a good thing. This I didn't. I'm not sure.
Let's skip
Yeah,
this.
yeah. And then
This is not a concern.
yeah. And the scoring parameters, they observe that when increasing alpha, which means they put focus more on the slice error, and the slice size would increase. So
Okay, keep going.
yeah.
Yeah, this is not a concern. But anyway, it seems that it seems to me that their experiment is really solid and comprehensive.
Yeah. And
okay,
then
let's keep the runtime. Let's keep the runtime
Yeah.
evaluation. So that's also not a concern.
Yeah, and then the scalability with upsize the rows or even upsize the columns, they prove that it's
scalable,
good.
right?
Yeah. So that's all.
Yeah, so for this approach, actually, I'm not sure whether they can be used, but I think this is supposed to be another debugging technique. And here you can see they are saying that they're debugging, right? But usually debugging would lead to a root cause.
I see.
And what do you think? And whether the approach can lead to the root cause? So basically, they just formalize the debugging program into a. I think that's just one step towards the root cause, right? So usually, for example, if you want to debug, the ultimate goal is that we know the program is an error, and we want to have a fix for it so that the program can work well next time. And the debugging is actually, even for debugging, it's not an end-to-end process because we just want the root cause, and there's still an open question how to fix it. And as for this paper or this work, they even didn't finish the process of debugging. They just pinpoint that what slice or what part of the data is more erroneous, right? And that's all. And so what? And do we remove this part of the data, or we need to keep retrain the data? And what is the follow-up solutions? The authors discuss this kind of question. So they basically just okay.
But I think their main contribution is to formally define this problem and make it be able to scale to run on.
Yeah. I think that's a very fundamental.
Yeah.
Structure work.
Yeah, and in the end, they also suggest maybe future work could be some priority-based enumeration or slice finding for not for accuracy.
So yeah, I'm not sure whether we need to adapt this, but we have a model management system, right? So the model management system will support a variety of queries. Maybe anyway, the slice is basically it's just a query. Maybe we can consider that kind of query in our own system. But I'm not sure. Let's keep going on to see the real problem. But anyway, it's a very interesting paper to discuss this. Okay.
Yeah, that's all.
Yeah, so I assume that there's no question here. Let's thank Xianglin and Siang Hwee. So both of them actually present very excellent presentations, and we can see the fundamental effort. So non-trivial effort they spend to prepare the presentation. Okay, let's call it a day and thank you very much. Bye.
Bye.